All right, in this video, we're going to review the properties of a vector space, a linear vector space, and then we're going to define what's the dot product. All right, so over here on the sheet of paper, I've listed or I've defined what a vector space is. So a vector space consists of a set, and the set will be the set of vectors, and it's equipped with an addition operation, so you can add elements of V, you can add the vectors. And it's also, you can also multiply vectors by scalars. And then this will be called a vector space provided the elements of V together with the addition and multiplication by scalars satisfies these 8 axioms, or 8 properties of a vector space. And we're going to go through them briefly, and then I'll demonstrate at the same time some of them in MATLAB using the vectors that we've defined already. Using the vectors which are defined as lists of numbers, ordered lists of numbers or columns in MATLAB. Just to remind you, I guess the first property here is that A plus B is equal to B plus A. In other words, the addition of vectors is commutative. It doesn't matter the order in which you add things. That's true for vectors. So to give you a counterexample of a case where that's not true, the operations of putting on your socks and your shoes, this is something that is not commutative. It's not the same thing to put on your shoes then your socks as it is of putting socks then shoes. All right, so for that case, it really matters the order in which you do it, but for vector addition, it doesn't. So let me remind you what vector addition is so that this property will be obvious. So if I have 2 vectors, let me write it on this side here. If I have 2 vectors, A defined as A1, A2, to AM, and a vector B given by B1, B2 up to Bm, then the addition then A plus B, this is the way it's done in MATLAB, is A1 plus B1, A2 plus B2, all the way down to AM plus Bm. So this is the way we do the addition. We just add the components of the vectors. So we're going to show that this addition rule for these vectors, which happen to be in this case ordered sets of numbers, that they satisfy the commutativity property of addition. And we're going to demonstrate it not just by adding, which is obvious and kind of boring. We're going to show that it is also true of vectors viewed as arrows in space. So to demonstrate this, I've created 3 vectors in this script, A, B, and C. They're all vectors with 2 components, and I will plot them. So I'll start out by plotting the vector A over here. So this is the vector A, and to this I'm going to add the vector B. So vector plot B, and the rule of addition is you go from tail. At the tip, you put the tail of the vector you're adding at the tip of the first vector. So the position is going to be the tip of vector A, and I'll plot this one in red. All right, so the result here, this point from 0 to this point, is the vector A plus B. I did A, then B. Now I'm going to do it the other way around. So first I'll plot the vector B in blue. So this is B, to which I will add the vector A. So A, I put the tip of A, the tail of A at the tip of B. And I get back the same answer. So regardless of whether you go A plus B or B plus A, you get the same answer, which is clear for the simple addition of numbers I have over here, because the order of addition, 2 plus 3 is the same thing as 3 plus 2, right? We were used to this commutativity rule for addition of real numbers, and it is also true of vectors. As we'll see later on when we do matrices, the rule of multiplication of matrices does not commute. So in general, it's not going to be true in that case that A times B is the same thing as B times A for matrices. But let's not get ahead of ourselves. Let's keep going through the different rules for a vector space. So this is the commutativity of addition. There's also an associativity rule, so that if we want to form the sum of three vectors, it doesn't matter if we first add b plus c and then to that add a, or add first do a plus b and then add c. So I will demonstrate both of these using the same vectors a, b, and c I have defined over here. All right, so let's clear all and define my vectors. Here's the vector a, to which I will add the vector b plus c. So vec plot b plus c, and I add that to the vector a, so I'm going to put the result of b plus c, the tip of that, the tail of that, at the tip of a. And I'll put the result in red. All right, so b plus c is in red, a is in black, and this is from here to here. That's the result of a plus b plus c. Now I will do it the other way around. I will first plot a plus b, and to that I will add c. So vec plot a plus b, and I'll plot that one in blue. All right, so this is b plus c, and to that I want to add c. Sorry, this is a plus b. I hope I said it right. This is a plus b, to which I will add c. So that means I stick the tail of c at the tip of a plus b, and I'll plot that one in red again. And we end up back in the same place. So I can do a plus b plus c. That is this path going from here to here is the left-hand side. Sorry, no, it's the right-hand side. Is a plus b plus c. So this is the left-hand side. So this a plus b plus c, the left-hand side. And now for the right-hand side, I have a plus b plus c. And you get the same answer. So that demonstrates the second property. All right, the next one is that there exists a zero or an identity element for the addition, which is the zero vector. So if you add the zero vector to a, you get back the a vector. So there has to be a zero vector in the set V of vectors. Also, every vector has an inverse, and we denote it by minus a. And the definition of the inverse is that if you add a plus its inverse gives us the identity, which in this case is 0. So a plus minus a is 0. This is the property we use when we want to subtract vectors. We also have these axioms that relate to multiplication by scalars. So if lambda is a scalar, just a real number or a complex number, and we multiply that to the addition of two vectors. So if we first add a plus b, then scale it by lambda, it's the same thing as first scaling a and scaling b and then adding the results. So that's the distributive law of scalar multiplication. There's also a distributive law that goes the other way, in which you can add two scalars and then multiply by a. So if you first add the scalars and multiply by a, it's the same thing as multiplying a by the scalar lambda and multiplying a again by the scalar mu and adding the two together. This is true, you get the same results. Computationally, in terms of the amount of work done by your computer, is not the same, because if a is a really, really big long vector, suppose a has 1,000,000 elements, well, if you do this side, you add two real numbers and then you do 1,000,000 multiplications. But over here, you do 1,000,000 multiplications by scaling a, followed by 1,000,000 multiplications by scaling a by different numbers, and then you do 1,000,000 additions. So this one is computationally is going to be much more efficient, but the result will be the same. There's also an associative law for multiplication by scalars, so I can do lambda and mu first, multiply those, and then take the result and scale a, or I can scale a and then scale it again by lambda. And the last one is that there's one is the identity for scalar multiplication, that 1 times v gives us back v. Okay, so these are the axioms of a vector space. Now I want to define the dot product, also known as the scalar product or the inner product. These are all different names for the same thing, as satisfies these properties. So there's a commutative, so it doesn't matter if you do a dot b or b dot a, you get the same answer. A dotted with lambda b is equal to lambda times a dot b. So you can scale b and then dot with a, or you can dot a with b and then scale with lambda. You get the same answer. There's a distributive law, a dotted with b plus c is equal to a dot b plus a dot c. And then the final one is that a dotted with itself is going to be greater than 0 unless a is equal to 0. So these are the properties of the dot product. The way it's defined, or the way we compute it, given the vectors a and b as these ordered lists of number, is the following way. So we do a dotted with b is going to be equal to the sum of ai bi over I. In other words, up to n. In other words, it's equal to a1 b1 plus a2 b2 plus all the way up to an bn. So you can verify that this rule satisfies these properties, so that this rule is an acceptable dot product for a vector space. I want to show how we compute it in MATLAB, how we do the dot product. So there's different ways in which you can do the same operation. Clear all, oh no, not clear, I want to keep my vector. So I have the vector A and the vector B, and if I follow this rule, the dot product of A with B should be minus 3 times 2, which is minus 6, plus 3 times 4 is 12, so the answer should be minus 6 plus 12 is just 6. So if I do the dot product, dot of A and B, I get 6 as expected. So that's one way of doing it. So dot A and B, that's the first way of doing the dot product. Another way is I can do what's called the transpose of A, and then multiply that by B. Do the multiplication, so A transpose times B. So what does A transpose B means? Well, if A is a column vector, defined up here, then A transpose is going to be a row vector. A1, A2, all the way up to AM. So in MATLAB, we distinguish between rows and columns. So if you'd have the row, and then you multiply this by B, and in MATLAB, that's a little star operation. In algebra, we would just write, on a sheet of paper, for example, just write AB like this. Then what this is equal to is the dot product, is A dotted with B. So that's another way of doing it. We can also do it the other way around. Since the dot product is commutative, I can do A dot B or B dot A. I can also do B prime multiplied by A. I could also multiply element-wise. I can do A1 times B1, A2 times B2, and then sum the result. So I can do sum of A dot star B. So the dot star in MATLAB means do the multiplication element-wise. Don't do a matrix multiply, do an element-wise multiplication. And then I do the sum operation. So all these are different ways of computing the same thing. So I should get a row of 6, so all of them gave us the same dot product. All right, so the nice thing about the dot product is that we can use it now to define a length, and with length we can take ratios of lengths and we can get angles. So because of the property that A dotted with itself is greater than 0 unless A is equal to 0, then I could define the length of A. So this is the length of A is just the square root of A dotted with itself. So this defines the length. Defines the length of a vector. And we can also use that to define angles. So if I have 3 vectors, A, B, and C, and such that A is equal to the sum of B plus C, and now I dot A with itself, so I get A dotted with itself. That is just going to be the length of A squared. And I could also do B plus C dotted with itself, and then use the distributive rule, right? That I could distribute the A into the sum of the other 2. I'll get B dotted with B plus B dotted with C plus c dotted with b plus c dotted with c. And this is the length of b squared. This one is the length of c squared. And these two, b dot c is the same thing as c dot b, is equal to 2b dot c. And both of these are equal to each other, right? So if a is equal to b plus c, that means that this a, the length of a squared is equal to this. So therefore, a squared is equal to b squared plus c squared plus 2 times b dot c. Now, if b dot c is 0, so if b dot c is equal to 0, then a squared is equal to b squared plus c squared. So the length of a squared plus b squared is equal to, the length of b squared plus the length of c squared. This is the Pythagorean Theorem. And that means that, this theorem applies provided that the sides of the triangle are perpendicular. So b and c have to be at right angles, and in which case this is true. So that means that if b dot c is 0, we can identify this with the vectors being perpendicular to each other. So if b dot c equals 0, then we say b and c are orthogonal. Or either perpendicular. And if we define, so this allows us to define the angle. So the cosine of theta, where theta is the angle between b and c. So if this is b and this is c, and this angle is theta, then we define theta to be b dotted with c divided by the length of b and the length of c. And this will give us the law of cosines, that the length of a squared is equal to b squared plus c squared plus 2ab cosine of theta.